Greetings once again, teachers and students far and wide, and welcome to AP Calculus BC Live with our second day of finding Taylor polynomial approximations of functions. We especially welcome our live viewers, and we particularly welcome those of you viewing on the West Coast. Wow, 6 a.m. You must really love calculus, because I know you're not up this early to see me talk. But we do welcome everyone that's joining us. If you tuned in yesterday, you witnessed Brian's extraordinary introduction to our ongoing topic by watching his cloning of his beautiful dog, Buddy. And he was able to develop the formula for finding a Taylor polynomial. And today we're going to focus more on solving various kinds of problems that use those particular elements of yesterday's lesson. As you can see, I'm not sitting in my back porch. It's wishful thinking. I wish I was, but here in Indiana, we had a beautiful day yesterday at 80 degrees, and then some tornadoes decided to come through, and now we have a high today of 48. So it's just kind of wishful thinking for some better weather here in the Midwest. So as always, you can find our documents in the description underneath each video, and we always encourage you to work along with us. We can't say this enough. We seem to say this over and over again, but we typically do write. Brian takes the lead in writing the predominant amount of our questions, and we typically will write more questions and post them into the Dropbox than what we plan on doing in our live streams. So that makes for wonderful e-learning experiences for students far and wide, and then eventually solution keys will get posted, as you guys have probably been aware by now. My name is Tony Record, and I'm an AP Calculus teacher at Avon High School. And I noticed the last couple of days, a sort of melancholy has fallen over our home. And it's particularly centered around a special member of my family. And that is my dog Wimpy. And I guess my dog has kind of been along by my side almost every single day. In fact, she's just right here below my feet sleeping. And I guess my dog has been hearing a lot of love given to Brian's dog, Buddy, in the last few days. And I was able to do a little dog whispering. I found out that Wimpy just wanted her time. So this is my dog. It's about a 10-year-old picture, and my dog is quite an older dog. She is now 16, which is like 112, right, in dog years. And this picture here was taken, not too long, about 30 minutes ago. And my dog is getting through life. She's about 80% blind and has lost most of her hearing, but we love her anyway. And she's always here with me every morning. And there have been times that I'm a little concerned whether or not you can hear her snore, because she can snore up a storm. So if you hear a little kind of vibration, kind of monotone in the background, that's probably Wimpy in her bed. All right. Also, I wanted to spend a little bit of time just kind of talking about some things that maybe kind of give you a little bit more insight into me. This is probably our last day together individually, because next week Brian and I are going to kind of team teach and take care of the review portion of the course. But I want to give you a little bit more insight to who is this guy that's coming into your computers every other day. And I thought the best way to do that is to talk about one of the passions that I have outside of mathematics. I've always sought this balance in my life. And that balance kind of focused around doing something that was a little bit more creative, like playing the guitar. It's something I've done my whole life, and I've played in several bands and cover groups and so forth. But one of the other things that I really truly enjoy is theater, and I've been very fortunate to be a part of an amazing theater organization here in Central Indiana, Hendrick Civic Theater, and have done several productions with them. So I just have some pictures of some of the latest productions. Lend Me a Tenor was one of my more recent roles. It was the most physical role that I had. It's kind of hard to believe that this is the same character, me, as this, but I kind of played a dual role in that particular production. Some of you might be a little bit more familiar with Arsenic and Old Lace. I was Mortimer Brewster there. Perhaps you've read as an assignment Pride and Prejudice. You could probably guess there. That's Darcy. That's a longer hair, and yep, real lamb chops there on the sides, mutton chops. My students ate that up for about 2 months that I had to wear those out. My most recent production, I think even Brian got a chance to see this one, was one of my most enjoyable shows called The Foreigner, which is a wonderful story about the senselessness of bigotry and prejudice. And then I was also in a production for a local playwright called Relative to Ransom. So that gives you a little bit of insight. And the reason why I'm bringing this up is that, there are things that obviously students are missing out because of the changes that are going on in the world. But I had just looked at my calendar, and in 2 weeks from today, I was scheduled for an audition for the upcoming production of Mamma Mia, which is now put on hold. But I'm hoping that they keep with the production and just kind of push it back a little bit, because that would be something that I would certainly love to do. So outside of that, about the only other talent that I have, it's not golf. Trust me, Brian has seen me play golf. I have an encyclopedic knowledge for 80s pop music. In fact, I challenge my students every year to go on the internet and find a song that charted in the top 40 at some point on the Billboard chart in the 1980s. And I can tell them the artist and typically the year that it was released and about the chart position that it peaked at within about 10. In most cases, many cases, I can probably tell them what key it's written in, because I played so many of those songs as a member of several 80s cover bands. So just some interesting, odd information about your AP Calculus BC instructor. Upcoming lessons, we've got our Finding Taylor Approximations today. Brian is going to close out our talk about Taylor polynomials tomorrow with the alternating series bound. It's really more of an extension of what we talked about yesterday and today. And they're your 5 first topics, I guess, of the following week that will center around our AP Calculus BC exam prep and review. Once again, you probably are already aware your AP exam will be Tuesday, May 12th. We want to make sure that we focus on that, mark your calendars. And the test will be made up of 2 free response questions. And I know Brian is hard at work putting together several what we feel to be potential looking AP questions. Of course, we don't have any way of knowing that, but we're going to do our darndest to try to get you prepared in the best way possible. So we're really looking forward to our sessions next week and those free response questions that we're going to send your way. Now, this is not a late April Fool's joke. We are going to kind of switch things up here a little bit on our warm-up. So if you do have the PDF that you're following along with, we're going to actually move to the guided practice example 1 first. What we want to do is really warm up properly. That's one thing I've known in 30 years of teaching and 20 years of coaching. It's very important to warm up. I've coached basketball, I've coached track and field. I was a track and field athlete in college. I've coached tennis and soccer, and I know that we need to warm up. So if we jumped into that AP practice problem too early, we could pull a brain muscle or something. So we've got to be very careful. So we'll take a look at this example 1 now. It says, find the 3rd degree Taylor polynomial for f of x equals sine of x, centered at x equal pi over 6. Use this polynomial to approximate the sine of 0.2. So what we're going to do is we're going to organize this a little bit. Brian went through the process of how we can develop this polynomial, and it focused very much on the function and its derivatives evaluated at where we're centered. So we're going to start, not that we need to write the original function because it's already there in the stem of the problem, but for organizational purposes, I will put it down. And then we're just going to set about to take several derivatives. So f prime of x would equal positive cosine of x. F double prime of x would be negative sine of x. And then at this point, we're starting to think, okay, well, wait a minute, when do we stop taking these derivatives? Well, we read through the problem here carefully, and we see that we're looking for a 3rd degree Taylor polynomial. So that's going to indicate to us that the 3rd derivative in this case is going to be a good place to stop. And that would be negative cosine of x there. All right, then I'll organize another column where each of these functions and their derivatives will be evaluated at where we are centered. And in that case, this is a pi over 6. So we think about, well, what's the sine of pi over 6? What's the sine of a 30 degree angle? And that turns out to be 1 over 2, 1/2. And then for our f prime of pi over 6, we're looking at the cosine of a 30-degree angle, right, which would be the square root of 3 over 2. And then by the time you get here, we're just going to really repeat some of the trig calculations that we've done, albeit with a different sign, in this case negative. And in the case of f triple prime at pi over 6, we'll have negative root 3 over 2. Right? Just one possible way that you can organize this. It's a very common technique that you might see in a lot of textbooks. Now, at this point, it's like going to IKEA, right? It's like buying some furniture. You just have to assemble this polynomial in the way that Brian had indicated yesterday. And it doesn't really matter what you call the polynomial. A lot of times we might use P for polynomial. I've seen capital T used for Taylor polynomial. You can pick whatever you'd like. We can use the subscript of 3 to indicate that we are taking this out to a third order, third degree, and we work from lowest degree to highest. And then the first term is just this constant 1/2, right? Now, technically, you could argue, well, isn't there some stuff with this? Well, yeah, you could argue the fact that you do have x minus where you're centered, all raised to the 0 power, all divided by 0 factorial, right? Well, the 0 power and the 0 factorial in this situation are just going to result in 1, and thus we don't really need that information there, but it does kind of tend to help understand how this polynomial will build upon itself. Then we go to the next term. We have the square root of 3 over 2. Now this time it's going to be important to introduce the rest of this stuff. We do need the x minus pi over 6 to the first power there. And we could put this all over 1 factorial, of course, but that 1 factorial is not going to really change the value of this, so we're going to choose not to write it. And then we keep moving on to the next term, which is going to be minus 1 over 2, right? But now we have a 2 factorial that we're going to introduce into that denominator. Whether you put the factorial there or not, it doesn't make any difference because we all know that 2 factorial is 2. And then once again, you have your x minus your c now raised to the second power. And then one more term, we finish up with the minus square root of 3 over 2. That 2 is going to have to be joined by a 3 factorial, or you could call it 6, or you could multiply it out and get 12 for this denominator, and finish it up with the x minus c, all raised to the third power. And there you've got your third Taylor polynomial. Now, this particular question wants us to go on a little bit further and actually approximate the sign of 0.2. And the way that you could do this, if you wanted to show really crystal clear, perfect notation, you'd want to be careful. You don't ever want to say that the sign of 0.2 is equal to the Taylor polynomial of third order at 0.2. We don't want to put an equal sign in between these, right? We could put an approximately, and that would be safe. And then we could say that this third degree Taylor polynomial is, well, we'll have to go to some kind of technology. And I've actually already typed it in for you. And I've done it actually in Zoom or Desmos, which might be a little bit familiar to more of you. It's a free online piece of software that you can certainly use. But there's our Taylor polynomial that we just computed. And I actually have the graph here sketched, I believe. And I can probably move this over if we need to see a little bit more of that polynomial. And then I've gone ahead and evaluated it. P of 0.2. Desmos does a good job of that. And you can see we get 0.1984. And I took the liberty of actually figuring out what the sign of 0.2 was, its exact value, or its exact value rounded to this many digits at least. And you can see that there's quite a bit of similarity. In fact, we don't start to disagree or, dare I say, diverge until we get to that fourth decimal place. So that would be what, 2/10,000ths of a precision. And that's going to bring up a very interesting point in what Brian can talk about tomorrow about, well, how good is this approximation? Now, he might focus a little bit more on alternating series, and this isn't an alternating series, but there are many other, well, one other particular way that you can focus on an error analysis when you don't have an alternating series, and he may touch upon that a little bit as well. And if you're curious, there's what the graph assigned looks like. And we can see that our polynomial coincides to an extent with that sign graph. Then if we also take a look at another way to maybe describe this situation is that we've got our function f of x equals sine of x, and I've developed a Taylor polynomial through the TI Inspire. It's just using a function that's innate to the TI Inspire. And you can see that I've got this slider set up that will tell me what degree of the polynomial I'm going to take. And right now, I'm probably at the worst possible degree we can. I've got a 0 degree, which is a constant, which would be, if you look at your sheet, that's going to be that very first term, 1/2. So my polynomial is p0 equal 1/2, and that's that horizontal line. But as you can see, as I increase that power, I start to see a brown colored graph here that starts to adhere much more closely to this sine curve. And you can see that the interval of convergence sort of grows for this polynomial. And I can take this up as far as I want, well, as far as I've allowed it to, and I think maybe I have it going up to about 15, and it's still looking pretty good in the screen that we see. All right, so again, if you didn't get a chance, that polynomial approximation was 0.198 if we decide to round it to 3 decimal places. All right, let's go ahead and take a look at example 2, if you would. And there again is Wimpy. This is from a few days ago, sending a message that April distance does bring May existence that my daughter drew on our driveway. And in this problem, we're going to find a second degree Maclaurin polynomial for the function g of x equals e to the 3x power. And we're going to set this up very similarly. But what I'd like you to do is I'm going to give you maybe about 30 seconds, and I'd like you guys to go ahead and list the desired functions g and its derivatives in a column for me, and let's check if we agree. Okay, let's take a look at your work here. It's one of the pitfalls. Sometimes just performing some of these seemingly simple derivatives can get us into trouble a little bit. So I'm going to start again by just rewriting the g of x just to organize. And did you notice that as you took these derivatives, you had to use the chain rule? So the derivative of e to the 3x would be e to the 3x times 3. We take another derivative, g double prime, and we would get 3e to the 3x times 3 again, but those two 3's could multiply to make 9. You can always check your inventory and make sure that you've taken as many derivatives as you need, and it says that this is a second degree Maclaurin that we're about to find. And the fact that it says Maclaurin is important because you know that that means that we're centered around 0, so I'm going to circle that information. So we're at a point now where we can just plug in 0 to each of these particular expressions. So we have g of 0, which is e to the 0, which we know to be 1, and g prime of 0 would be 3e to the 0, which is 3. And then, of course, g double prime of 0 is going to be 9. All right. Now we just assemble our furniture and we write our Maclaurin polynomial. We can still call it a p. It would be of order 2. And we start with our constant 1. That's the g of 0. And then to that, we add 3 times what could be x minus 0, but we'll just call that x to the first power all over 1. And then for our last term here, 9 would have to be divided by 2. And I'm going to go ahead and put that factorial there just to emphasize the fact that we are now starting to increase that denominator by an integral amount of 1 factorial. And then we have our x squared. And that should take care of that particular problem. There's really nothing else that we have to do. We're not approximating any certain value of e, although we could use this if we wanted to do that. If we want to take a look one more time at some technology for this particular problem, there's our function e to the 3x in blue. And I, again, have set up the template where I can compute a Taylor of that function f1 of x, where x is my independent variable. I'm going to take my order to be in. That allows me to let the order be whatever I want it to be. And that 0 is, you can probably guess, is where we're centered. So you can see how if I increase the n, if I take it up to 2, which is exactly what this problem called for, we have some nice looking convergence maybe in this area here. In other words, that polynomial might be pretty reliable to approximate a value on the function e to the 3x. Outside of that, I don't think I would rely on it a whole lot, but watch the graph, particularly the red graph, as I increase the order. Well, first of all, you kind of see it moving up and down, right? That's just going from an even power to an odd power, of course. But you can start to see how we move or meander along the left side of that curve just a little bit more and become more convergent in that negative direction if I take it up to n equal 20. All right. I think we're pretty warm. What do you think? I think we can go back to yesterday's warm-up problem, which is our AP practice question. Wonderfully written question by Brian. It uses a lot of elements of calculus, just not BC, but AB as well. So we're going to go ahead and read this very quickly. We have a function f, and it has derivatives of all orders for all values of x, and a portion of the graph of f is shown. And we have the tangent line to the graph of f at x equal 2. We're going to take g and let it be a function defined by g of x equal 3 plus the integral from 2 to x of f of t dt. In part A, you were asked to find the second degree Taylor polynomial for g of x centered at 2. Part B asks, does g of x have a local minimum, local maximum, or neither at x equal 2? Give a reason for your answer. And part C says to consider the geometric series, the summation of a sub n, as n goes from 1 to infinity, where a sub 1 is g prime of 2, and a sub 2 is defined to be p sub 2 prime of x minus 1. Now, it's possible, depending on when you downloaded this, we had to make a little correction to this. So this is now the corrected version. So it's possible that maybe you were struggling with part C if you were working on this a little bit earlier. But this is the way that we want the problem to read, and we'll go ahead and make sure we solve C carefully together. And then part C does say that we want to find that summation of a sub n when x is 13.6. So let's go ahead and dive into this for part A. Find the second degree Taylor polynomial. Well, one of the things that both Brian and I want you to make sure that you're aware of is just because you're presented information that's a little bit different, you don't want to make that change the way that you go about solving the problem. I tell my students all the time, don't let calculus stand in the way of you understanding calculus. Sometimes that throws them for a loop and they think that I've messed up. But just because calculus is presented in this problem in a different way doesn't really change our strategy. And by that, I mean, if we want a second degree Taylor poly for g of x, we're going to figure out, well, what is g of x equal to? And then we're going to figure out what's g prime of x equal to. And then we're going to figure out what g double prime of x is equal to, right? Because we know that we want that second degree polynomial. Well, the g of x, again, it might seem a little superfluous. I'm just going to write it down for organizational sake, but it's the expression, that function defined as an integral expression that was given to us in the stem. And now when we find g prime of x, look at how wonderfully written problem this is. You're going to use something from your AB portion of your course, where you're going to take the derivative of 3 plus this integral. And of course, the derivative of 3 is 0. And now you're using one of the forms of the fundamental theorem of calculus here, where you can just replace this dummy variable t with this upper boundary of x, and we don't have to enforce the chain rule because that upper boundary is simply an x. And then when we go down here to g double prime, we're going to end up taking the derivative of f, which we know to be f prime of x. And I'll tell you what I'm going to do. I'm going to rewrite this f of x just a little over here to the left so we don't confuse that lower boundary as maybe being a squared around it. That's never happened to me. So anyhow, we're going to go ahead and plug in the 2 for the x. So when we solve this, g of 2, we're going to replace the x with 2, right? We're not going to let this calculus stand in the way of information that we know. We know to evaluate this function whenever x is showing up, we're going to replace it with a 2. So we know that the integration that has a lower boundary and an upper boundary that are the same, that's going to be 0. And then we just end up with 3 here. All right, so you can see that you're going about finding these components of those coefficients for your polynomial in a little bit of a different way. Maybe this is a way that might be more akin to the exam that you're going to see this year, because there is no photo math that's typically going to help you find these coefficients. You have to have the conceptual knowledge of knowing how to put them together. So what is g prime of 2? Well, I'll tell you what g prime of 2 is. It's f of 2. So we have to think about, well, where would we go to find an f of 2 value? And what better place than a graph of f? That's what this particular function is graphing, the function f, and it's all of its derivatives. The portion of graph of f is shown. And we see that f of 2 is going to have this y value that's equal to 1. And then finally, g double prime, also known as f single prime, evaluated at 2, is going to cause us to look a little bit deeper into this tangent line. And we have to have that conceptual understanding that says, okay, well, that means that we want to figure out what is the derivative of this graph at that point. And that just means it's the slope of the tangent line of that particular tangent line. So we have the 0.21 here, and we might have to look at this a little bit and maybe trust our eyes. It's a very well done graph, so it won't take a whole lot to see that you're just going to go up 3 units and over 1 unit. There is no scale change, and that's going to serve as that particular f prime of 2 value. So there you have it. You have all of the components. You can assemble your furniture at this point, and we see that we have p of 2, or p sub 2, I should say, the second degree polynomial. We'll start with our 3, our constant. To that, we will add 1 over 1 factorial. We take another quick look at this, and we see that this is centered at x equal 2. So we need to put x minus 2. There's no need to get rid of that 1 there. I know we don't need it, but we could leave it there if we'd like. And then we can add our final term, which is 3 over 2, or 2 factorial if you want, times the quantity x minus 2 squared. And there is your second degree Taylor polynomial. Brian made a good point yesterday about how a lot of times students tend to get a little scared about Taylor polynomials, even moving into Taylor series in a normal year. And it turns out that these really aren't that difficult. And I think they're one of the most enjoyable parts of the course, because they answer a lot of previous questions about, well, how does back in the day, how would we compute some of these more difficult sine of 0.2 e to the second power type of things without using a calculator. And this is exactly how our founding fathers did that. But it also kind of opens the door to answer a whole bunch of new questions about how you can integrate really super complex functions. Well, it turns out that we can rewrite them as Taylor series and then go about our integration techniques that we've learned. So it's a wonderful ending, I think, to your journey through your high school calculus. If we take a look at part B asks, does g of x have a local minimum, local max, or neither at x equal 2? Give a reason for your answer. Again, let's not let calculus stand in the way of the calculus that we know. It's likely that you are pretty adept at figuring out how to find local extrema. If the function here is g of x, we need to figure out what g's derivative is. So we're going to take the derivative of g. I know there's no traditional looking function called g. It's a more of a non-traditional type of function, let's call it. But again, we've already done this. We figured out in part A that g prime of x is f of x. So now what we have to do is figure out, okay, well, what's going on here at 2? Well, I want to say that we had already figured that out as well. We had figured out that f of 2 is equal to this 1. And so we have to rely on the fact that we can only have a relative extrema when your first derivative is either equal to 0 or possibly undefined. And because 1 is neither 0 nor undefined, we can say that g of x has neither. The word local and the word relative are interchangeable terms that you can use on the AP exam. So we'll say it has neither a local min nor a local max. at x equal 2. And that's going to give you enough insight. They're going to be able to look over here and see that you had justified that by saying that your derivative is equal to 1. But if you want to kind of polish this up a little bit, you could just simply say because g prime of 2 is not equal to 0 nor undefined. Okay. Let's move on to our wonderful part C. It's probably my favorite part of the question. It says, consider the geometric series, the summation of a sub n, where a1 is g prime of 2, and a sub 2 is p sub 2 prime of x minus 1. We are asked to find the summation of the a sub n expression when x is 13/6. So the first thing that we want to look at this is kind of understand, what is this question saying? It's saying find a summation. That means you're going to add up a bunch of infinite things. Well, wait a minute. We can't do that unless we have what kind of a series? Geometric, which, okay, that's making sense. So we're going to have to rely back on our geometric series knowledge in this particular problem. Now, geometric series are typically very easy to add, but you have to know a first term, which it looks like we're kind of in the door there. But you also have to know the value of r. If you remember, the typical form looks something like this. You have a term and then an r to a power, and this can kind of serve as your basis of building that formula. Well, the r value in this problem is just going to take a little bit of thinking. We have to really have that conceptual understanding of what is the r really saying? Well, it's what you would multiply a1 by to get to a2. So if you wanted to solve that for r, right? If a1 times r is a2, basically, right? Then solving for r is nothing more than just dividing by a1. So there is what you've got. Okay, well, what does this mean specific to this problem? Well, the a2 happens to be p sub 2 prime of x. P sub 2 prime of x. Well, what's p sub 2 prime of x? Well, if you go back to part A, I think you're looking at a p sub 2 right there. And I'm not going to flip back to it. Perhaps you have it on your page, but if we take that derivative, we should end up getting 1 plus, and then we would have, let's see, well, maybe I should go back and look at it just to make sure, because you might be just following along here. But what we would see is the 2 and the 2 factorial here would cancel, and we would have 3 quantity x minus 2 to the first. So 3 quantity x minus 2 to the first. There is no chain rule that we have to worry about because the derivative of x minus 2 is 1, of course. And then please don't forget, there is a minus 1 here, kind of sitting here at the end of that a2 expression. And then we would divide all of that by a1. Well, a1 is g prime of 2. And I want to say for the third time in this problem, we're going to use the fact that g prime is the same as f. And if we evaluate it 2, we're looking at that 1 again. So the denominator is just simply a 1. Well, now we would like to evaluate this very specifically when x is 13/6. So what do we get when we do that? Well, these ones on top cancel. We have 3 quantity 13/6 minus 2, which is really 13/6 minus 12/6 or 1/6, and 3 times 1 over 6 would give us 1/2, right? So a little bit of work, but that was our r value that we needed. And pretty much that does the bulk of the work for us, because now for the summation of that a sub n expression, all we need to do now is just to realize that we take the first term, right? Well, let's go ahead and compute what that first term is going to be. And that first term is, well, that first term is 1 in this case, right? We're getting 1, and then we take 1 minus our 1/2. And once we simplify that, 1 over 1/2 is going to be 2. All right, so that takes care of our part C. All right, now we're kind of a little bit off kilter here, so I'm going to go ahead and give you this lesson overview now that we're about halfway through the lesson or more, but we're just continuing to investigate the importance of Taylor polynomials. That's what we're doing. They play a very vital role, not just in the world of calculus, but in the world of mathematics as a whole. And we're certainly going to be solving very unique conceptual based problems with these Taylor polynomials. What you should know, obviously, how to develop a Taylor polynomial from a given function. We've done that 3 times already. Yep, the difference between a Taylor and a Maclaurin is very important. One is centered at 0, the other's not. And the components that make up the coefficients of the terms in the Taylor polynomial seem to be a little troublesome sometimes for students, remembering those factorial values each time. And there you can see another potential question that you could answer given a 4th degree Taylor polynomial with this elusive k here. They can ask you to find the value of k given some information. So let's do this. Let's go ahead and continue a bit with our guided practice. And we could certainly have us take a look at example 3 here. It's a problem that's got a little bit different modality. You're looking at problems or information given from a table. So what I would like to do is I'm going to start the timer. And I'm going to have you kind of read through this on your own and see if you can start to generate those important function values and maybe even get as far as evaluating them at where we need to evaluate them. So I'll give you about a minute to think about this while we play Kareem's wonderful music. It's kind of like being on Jeopardy, isn't it? Just with different theme music. Now, as you read through this problem, hopefully you came to the realization that there really is no function, g of x, that you're going to end up taking derivatives of per se. You're going to actually start diving right in to those specific functions evaluated at 3, if that makes any sense. So if we need a 3rd degree Taylor polynomial, and we are centered at x equal 3, then as I said, we could just jump right in and say, okay, well, what is g of 3, right? We don't have that blue column that I used before, g of x, g prime of x, g double prime. So we look at this and we think, oh my goodness gracious, how are we going to find g of 3? That looks absolutely impossible. Well, that's what the chart is for, right? We see our g of x, we see our x value 3, and we can deduce very quickly that g of 3 is going to be 4. Now we go to g prime, and we're starting to really get very fond of this chart because we see a g prime of x as -5. And then we know that we have to take a couple of more derivatives. So g double prime comes next. And then, sadness breaks out because we can't use the chart anymore. But if we read very carefully, it does say that once n is equal to 2 or larger, and that is where we are now, then the nth derivative of g, it's x equal 3, is given by this expression. So we could just take that 2, which is our n, plug it in here. So we have f of 2 minus 2, which is f of 0, the 0th derivative, which is just the original function f, right? Evaluated at 3. And then lo and behold, we're back to the chart. One more time for g triple prime of 3. If we allow this n in this expression here to be a 3, now we have f's first derivative evaluated at 3. And it turns out that we can use the chart there as well. And we do have this decoy value. This f double prime never got used, but it's nice that it's in the chart to sort of keep us on our toes. So if we write our Taylor polynomial, so p sub 3, I believe, is what we want of x. We assemble it 4, then we subtract 5 divided by 1 factorial. We don't need to write that, and we know that we're centered at 3, so we're going to go with x minus 3 to the first, and then we just proceed from there. 1 over 2 factorial times x minus 3 squared, and lastly, minus 2 over 3 factorial x minus 3 cubed. And again, it's your prerogative. If you want to reduce these, you can. Just if you reduce them, make sure that you reduce them correctly. But there's nothing wrong with leaving that as 2 over 3 factorial or even 2 over 6. Okay. Several wonderful problems here. Example 4 here in the guided practice is going to be something that we are going to assign for homework, but it has a lot of similar characteristics to the problem that we just did. And if you couple this with example 5, which is another wonderful table question, it again has some similar characteristics. And so you could use your knowledge that you gained from doing example 3 to help there a little bit. I would like to turn our attention now to the check for understanding problems and look, let's look specifically at number 2 here. Number 1 is a very well-written problem as well. They all are. But I'd like you to kind of do some struggle with number 1 a bit because it's got some kind of elements to it. The value k, which kind of is not the most common expression that you might see for a function, but that sort of is the overriding theme. You've got this graph of k and a tangent line. Does that sound familiar? Well, we did see a problem that was a little bit like that at the very beginning of the lesson today, and maybe you can kind of bridge those together. But I really enjoy this practice number 2 that I'd like to work through with you. And it says that they've got the functions f, f prime, and f double prime. They're all continuous, they're all differentiable, and the nth derivative of f is given by yet another expression here. Nth derivative of 1 is the summation as I goes from 0 to infinity of 12 times the quantity n minus 1 over 5 to the I power. And so if you can't read these real well, make sure that you understand these are the letter I. It's the index in this problem. And that particular function's derivative equation is only good for a certain time when n is between 0 and 5. We're asked to find the third degree Taylor polynomial for f of x, and we're centered around 1. So again, the key components here, we have a third degree Taylor. We are centered around x equal 1. We once again find ourselves in that same boat. We don't really need to list f of x and f prime of x and f double prime of x because we don't really know what they're going to be generally, but we do know what they're going to be very specifically. And if we start with f of 1, well, we start with f of 1. Well, what does that really mean? Well, f of 1 means that we could actually go into this formula and we can replace the n with a 1. So upon doing that, we have a summation expression as such. N is 1, so 1 minus 1, of course, is 0. Well, by the time you take 0 and divide it by 5, you get 0. And if you take 0 and raise it to any power, you're still going to get 0 there. And we're at a situation here where we're going to get 0 as this first particular value. Actually, yes. We're adding 0 several times. Now, if we go to f prime of 1, if we go to f prime of 1, that means we're going to replace this n with a, and actually I'm going to need to back up, you guys. This is what happens when you get kind of old. F of 1, what is the derivative of f of 1? I actually jumped the gun and I was doing f prime. I was seeing if you guys were paying attention. Let's redo this. F of 1. This is really the 0th derivative. I'm going to plug a 0 in for the n. Let's try that. So what I should have here for f of 1 is I going from 0 to infinity, excuse me there, 0 to infinity. And then I should have 12 times negative 1/5 times I. That's what I want there. And it's unfortunate because this is going to be a little harder to add, unfortunately. But we are able to do it because this is a geometric series. So we can see that the first term, if we let I be 0, is going to be 12. And hopefully we all realize that the radius, or the ratio, I should say, the ratio is negative 1/5. So 1 minus the ratio is going to be 1 plus 1/5, which we know to be 6/5. And then if we multiply by the reciprocal of that, I believe we get 10. So f of 1 is 10. Now let's do f prime of 1. If we do f prime of 1, we can then state that the n is 1, and that's where our 0 comes from. And this one is a whole heck of a lot easier to add because you're just adding 0 plus 0 plus 0 many, many times over. Okay, how far do we have to go? Well, we have to go up to, we have to go up to a third degree. So f double prime of 1, remember we're centered at 1 here, is going to allow us to let the n be a 2. So the summation is going to look a little something like this now. We have 12 in front. 2 minus 1 is positive 1, so we have 1/5 to the I. And now you have another series that still is a geometric series that you still can use the formula for. And you always have to keep careful sight of the fact that that ratio, that R, has to be less than 1, has to be strictly less than 1. So our first term is still going to be the 12. And if we take 1 minus 1/5, looks like we have 12 over, what would that be? 12 over 4/5. And if we multiply by that reciprocal, I believe we're going to get 15. Okay, boy, I'm glad we only have to do one more of these. F triple prime of 1 is, again, pretty much going to result in a similar situation where now this n is a 3. 3 minus 1 is 2. We have 2/5 to the I. And again, as long as this R value is less than 1, we are free to use our first term divided by 1 minus the ratio each and every time. And it turns out that this time we get 12 over 3/5, which I believe is 20. Now, if I go back to this, do you kind of understand why this restriction is in place? It's really important because if we were to expand that restriction and say let n go up to like maybe even 6 and 7, we could have an issue with trying to add this, right? We're trying to add an infinite series here, and that could be a little bit problematic for our n value. But if n is 5, we're still safe. But by the time n is 6, we're going to have a 5 over 5 here, which is equal to 1, which loses our possibility of convergence. All right, we still have to write the polynomial, but that's pretty academic at this point, and it's very likely that you're becoming quite good at it at this point. So we have p sub 3 of x is equal to our 10. Now this is kind of interesting, and I wanted to make sure that we finish this problem, is that you have this sort of missing term, right? This first degree term, the first power term is going to be gone. So we want to skip over him and make sure that you pick up where you left off and you use a 2 factorial for the denominator of this 15. And of course, the x minus 1 would have to be squared there, okay? And then we write up our last term, and we have to remember that we need a 3 factorial for his denominator, and we have x minus 1 raised to the third. Okay. Again, Brian and I always talk about how there's just so many neat problems here. We just want to work with them and share them with you, but we do find that we run out of time. Sometimes teaching Calc BC in a 45, 50, 55-minute time window is always a challenge. And if you're a teacher out there that teaches BC, I think we're preaching to the choir there. But practice number 3 here is a wonderful 2-part question that throws in this odd, even, piecewise function that's going to throw just another twist on the way that you're going to figure out some of these coefficient values. And then we have this wonderful problem 4. These are among my favorite questions. I use a lot of these kinds of problems with my own students where they have to extract a certain value within a given Taylor polynomial to figure out what the true derivative value, in this case, f triple prime, is going to be. So you certainly want to take a look at this one. It really doesn't take a lot of time to solve, but it can be very tricky. So check this answer. And then I love this one. The last problem, consider this function g of x to be e to the negative 2x over 3 and find the coefficient of the x to the 26th term. I advise you to not take 26 derivatives. There is a better way, and I'm sure that you probably find that way if you kind of spend a little bit of time with it. So it's a wonderful question as well. So in the summary, our enduring understanding doesn't really change. Power series will allow us to represent an associated function on an appropriate interval. And our takeaways, just like yesterday, Taylor polynomials allow us to approximate values of more complicated functions. In many cases, we have seen as the degree of the Taylor polynomial gets larger, the polynomial tends to be a little bit more reliable, and it will approach the original function over a growing interval. And Taylor polynomials can always be extended to Taylor series that leads to the idea of the power series, which, although is not a testable component on this year's AP exam, it's always something that you can revisit. And if you hadn't had a chance to learn that in your own physical classroom or virtual classroom, it's something that maybe you can visit after the AP exam. Common pitfalls: sometimes students forget that the coefficients of the terms of the Taylor polynomial are of the form the nth derivative evaluated at where you're centered over the n factorial. So you mustn't forget that there's that n factorial component that makes up that coefficient. And Taylor polynomials can always produce approximations, but we haven't learned how good these approximations are for our desired function yet. But you're honestly about 23 hours away from that if you're going to watch live, because Brian's going to do a great job of kind of putting that component together. AP practice, so your other little homework assignment tonight is just a small 3-part question here where you have a function of all derivatives and orders for real values of x. We're going to tell you that the second Taylor polynomial, the second Maclaurin polynomial for f is going to be defined as p2 of x, and we're going to tell you that f of 0 is 1, f prime of 0 is 0. If p sub 2 of 1 is a half, we want you to find that second derivative evaluated at 0. Kind of ties into understanding how to build those coefficients. Part B is going to ask you to find p sub 2 prime of 0 and p sub 2 double prime of 0. And then we circle back to some AB knowledge. Does p sub 2 of x have a relative min-max or neither at x equals 0? Explain. And then finally, we want to use the p sub 2 of x that we had before to approximate f of 1/2. Our tweet outs are still coming in fast and furiously, so we want to recognize the AP Teachers Rock tweet of the day. And this comes from a group of students that say, "Thank you to my AP Calculus teachers, Mrs. Heil and Mrs., and I am sorry I will butcher that, but maybe Zayek, for showing me the wonders of calculus, which I now love, caring about their students, being great teachers." You can't ask for anything else than that. And Mrs. E, again, I'm sorry if I've mispronounced that name. And as far as our AP Students Rock, well, I'm a little biased on this one, but this comes from a really good friend of both Brian and I's. My AB students are working so hard during our e-learning. I am so proud of them. And this comes from a teacher extraordinaire from West Florence High School in South Carolina, Vicki Carter. Vicki, thanks for all that you've done for the AP community and for Brian and I. We really appreciate you. Again, we always want to make sure that you're aware if you or your friends are having some trouble accessing equipment that they can use for these e-learning lessons, or by the time they take their AP exams in all subjects, or if internet is a problem, please have them reach out to the College Board at cb.org/tech, and they'll certainly do their best to take care of all the issues that you might be having there. They're really wanting to work with you on that. And we want to thank you for watching. We hope you'll join us again. Tomorrow, Brian is going to be in to wrap up our last lesson that's kind of teaching the new content, but he's going to really put a nice finale to our study of Taylor polynomials. And we're going to take you out with our outro music by our good friend from New York. We want to thank Anthony G for this wonderful outro music. And until then, I want you to stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes, AP Calc.